So today we're going to talk about exponential functions, and exponential functions take on the form that look like this, where the x, or the variable, is in the exponent. So the a is considered the base of the function, and the a, we have some stipulations on what a can be. A is going to be a positive number, so a greater than 0, but a cannot be equal to 1. And the reason why a cannot be equal to 1, because if you have 1 raised to any power, it's always just 1, and it wouldn't be an exponential function. It would end up being a constant function, because you would just have a constant line at 1. So we can't have the base of 1. So here are some examples of what exponential functions look like. So here we have f of x is equal to 2 raised to the x power. The base here is 2. We have g of x is equal to 3 raised to the x power, where the base is 3. Here we have h of x is equal to 10 to the x power, where the base is 10. And here I have j of x, which is equal to 2/3 raised to the x power, where the base here is 2/3. Those are all exponential functions, and when we exponential functions share some characteristics, and what we're going to do is we'll take a look at the graph. So what I'm going to do is I'm going to look at one of those functions. I think I called it g of x, but let's just call it f of x is equal to 3 to the x power. And we're going to create ourselves a table. And then from that table of points, we can graph the function. So I'm going to select x values. Now remember, the base has to be greater than 0. So the base of 3 is greater than 0, so that's an exponential function. But my x value can be any number. So I'm going to pick some numbers. I'm just going to pick some numbers around the origin. I like to usually do from the ones that surround the origin. So I'm just going to pick some x values. And what we're going to do, you can pause and you can calculate what the y value, or f of x, the output would be when you plug in the x value. So, for example, let's do the first one together. If I plug in -3 for my x, so that means I have an input of -3. 3 to the -3rd power, remember what the negative exponents do? They make the base go to the denominator and the exponent turns positive. So this would be 1/27, or 1/27. Now if I put 1 divided by 27 in my calculator, I'm going to get, so I'm doing this because I want to be able to graph this, and I don't know what 1/27 is, but I need a decimal approximation, which is 0.037. And then I would do the same thing with all of these. So pause the video here, calculate what it would be when you input this, and then write your answers here. And then if you do get any fractions, simply give a decimal approximation so that we can graph it, because the next step we're going to do is graph the problem. Okay, so I found my values, and then my decimals here would be 0.11, and here we'd have the 0.33. These are run-on decimals, all of them, both of them. And then let's plot these points on graph paper. So -3 point that's very close to the x-axis. And I've got 0, 1. And we've got 1, 3, 2, 9, 2, 9, somewhere up here. And I'm not going to be able to plot 3 27. So, but we get the look of what this looks like. So an exponential graph has this, it's not a straight line. It gets very closer and closer to 0, and it rapidly increases as I go to the right. So it's going to look something like this. And exponential graphs will have this rapid increase, rapid growth there. And so, but I also want to point out some things about this graph. We have a domain here. You can put in any x values. Notice though, you don't get y values that are negative. So the range is going to be all positive real numbers. The other thing that we're going to see is if our base is between 0 and 1. Remember, our base can't be 1. It has to be a positive number, can't be 1. But what happens when our base is between 0 and 1? And so to explore that, let's take a look at the graphing calculator. And so here's my graphing calculator. And the first thing I'm going to do is I'm going to put in the graph we just did by hand. 3, and then caret symbol x, and then hit graph, and you'll see this similar to what we drew. You can also view a table by hitting second graph, and you can view the points that we just came up with. You can see them right here. Now, instead, what happens if my base is between 0 and 1? So I'm going to say my base is, what if it was 1 over 3? Caret symbol x. So 1/3 raised to the x power. It's going to be this red line. It's going to be a decreasing graph. They do have some common characteristics. So this one has a rapid decrease, where this one has a rapid increase. They both don't cross the x-axis, so they form a horizontal asymptote. A horizontal asymptote is formed at y equals 0. They both, if I zoom in here, let me change my window. Change our window so that we can see a closer up view. They both intersect at 0, 1. Because when you plug in 0 for your exponent, you're always going to get the answer of 1. Remember, that was one of the rules of exponents. If you have a 0 exponent, no matter what the base is, you're always going to have an output of 1. And so you see that reflected here. So let's kind of sum up these characteristics of exponential graphs. And we can sum it up here. And let's fill in the blanks together here. The domain. When you have the function f of x is equal to a of raised to the x power. On here, on this little graph here, we're using b as the base, but you could use any letter, doesn't matter. Our book uses a, so we will use a. The domain, I already mentioned this, the domain consists of all real numbers. In interval notation, I would write that as negative infinity to positive infinity. The range, your y values, your outputs will always be positive. So I'm going to say all positive real numbers. If I was to write that in interval notation, it would never be equal to 0. So I would have a parentheses because it's a open interval, 0 to positive infinity. The graphs of all exponential functions in the form of f of x equals a to the x power pass through the point 0, 1. So we were just talking about this because f at 0, so a to the 0 power is equal to 1. The y-intercept will be 1. and there is no x-intercept because it does not cross the x-axis. If the base is greater than 1, so now, again, our book uses a, so I'm going to say a here. If a is greater than 1, then f of x equals a to the x has a graph that goes up to the right, so it's increasing, and is an increasing function. The greater the value of a, the steeper the increase. And let's explore this, and you can explore this on your graphing calculator. So let's grab the graphing calculator and explore this, what they're saying. So I'm going to go here, and let's clear out this one that had the base between 0 and 1. And I'm going to now put 10 to the x. And I'm going to put 100 raised to the x power. And I'm going to take a look. And so take a look. We've got the blue line was the smaller number, the smaller base. The red line was 10. And the black line is 100. So the higher the base, the steeper the increase. Let's go back here. If the base is between 0 and 1, then this function, this exponential function, has a graph that goes down when you go to the right and is a decreasing function. So we saw that when we put in the base of 1/3. The smaller the value of b, let's see what happens. So let's grab the calculator. And so let's see. I'm going to clear these. And we're going to put in some different bases. So let's say 3/4. That's, and you can think of the decimal, that would be 0.75. Let's compare that to 1/2, that would be 0.5. And then let's compare that to 1/3. That would be 0.3. So the smaller the value of b, the black line is the smallest value of b. This has a steeper decrease. The smaller the value of the base, I keep saying b, but the base, the steeper the decrease. So the smaller the value of the base, the steeper the decrease. Also, our function, our exponential function, is a one-to-one function. And if it's a one-to-one function, then it has what's called an inverse. The graph, so in order to be a one-to-one function, let's imagine we go back to our whiteboard. In order for something to be a one-to-one function, first of all, it has to be a function, so it has to pass the vertical line test. So this one does. But in order to be a one-to-one function, it has to pass the horizontal line test. And this one does, meaning that each horizontal line I draw through here will only intercept the graph in one spot. And yes, when you get down to here, it gets kind of tricky, but actually it's moving closer and closer and closer to 0, and it's never horizontal. So it does pass the horizontal line test. So going back to here, that's what is meant here. And so when it is a one-to-one function, then it has an inverse. In this last line, the graph of f of x equals a of x, or exponential function, approaches but does not touch the x-axis. So it gets closer and closer to it. The x, or y equals 0, is a horizontal asymptote.